Okay, let's get started here. Section number 5, we will hopefully finish that up today. Maybe get into section 6.5, and then we'll do evaluations at the end of class. Are there any questions before we get going here? Okay, so we were talking about the place-kicking data set once again. And what we were trying to do was find the best, let's say, overall model for it, including any important variables that might be needed, transformations, interactions, all that good stuff. And we had gotten to a point where we picked a model that included distance, wind, change, PAT, and then a distance by wind interaction and a distance by PAT interaction as well. And what we were trying to do was look at, well, are there any maybe poorly fit observations or specifically explanatory variable patterns? Were there any influential observations? What's the overall, how well does the model overall fit the data? And basically what we ended up concluding is that there's definitely one problem point that we need to look into. And interestingly, it concerned what you see here highlighted in orange. Let me get my red pen out. Where it was number 119 and 120. They were, both of those explanatory variable patterns happen to be non-20-yard PATs. And typically in football, PATs are 20 yards. And we see, especially for number 120, the Cook's distance value of 0.31 was quite large relative to the other observations. For 119, it was kind of large too. And so what this leads us to believe is that, hey, there's something going on here. Maybe these observations are influential. And so we need to follow up on this to make that determination. So then that takes us to where we left off, which was page 99. What we need to do is look to see if these observations are truly influential. And the way to do that is you temporarily remove them from the data set, re-estimate the model to the remaining data, and look at your beta hats. Do they change compared to what we had before? Notice the emphasis here on the word temporarily. I'm temporarily removing 119 and 120. The reason why I'm doing both of them at the same time rather than maybe just one of them at a time is because I saw that they had a common characteristic about them. The fact that they were non-20-yard PATs. So, to estimate the model then without 119 and 120, it's very easy. I use exactly the same code as before to estimate the model, but in the data argument for GLM, I say I do not want rows 119 and 120. And the way to do that is to put a negative out there in the row indice and put in the rows 119 and 120. You'll verify that on your own that indeed that this basically just removes 119 and 120. And so this is what I get then after I estimate my model. That's in the top. And in the bottom is going to be what I had before with 119 and 120 in the model. So what has changed? Take a look at this right here. Before, distance in PAT had a negative beta hat. Its walled test p-value was 0.0056, indicating, yeah, this is important. But take a look at what happens when I remove just those two observations. Now my beta hat is positive. So that changes my interpretation of that interaction. And also take a look at my walled test p-value. 0.78. So these two observations are controlling whether or not, essentially, I should have interaction in my model. That's why, indeed, they are truly influential to the model's fit. Typically, you would not like, like one or two observations having that or dictating that much about your model. Because imagine, overall these represent just 5 overall place kicks out of 1,438 place kicks. So just 5 place kicks are saying, hey, you should have this interaction in your model. That's why these are influential. So given that, and given that, again, we don't typically want to have observations have that much influence on whether or not I have, let's say, a particular term in my model, I have some decisions to make about what should I do about this. So let me come back down here. So here are 3, well, I guess before I get to these 3 possible choices, the first thing that you should do is look, and this is not in the notes, this should be in the notes, but it's not in the notes. The first thing that you should do is, well, how about you put number 119 and 120 back in your data set, re-estimate the model, but without that distance and PAT interaction, and look what happens. I did that. And what I got was I had very large residuals, indicating the model was poorly fitting those observations. So that indicates to me that if I want to have 119 and 120 in my data set, I need that interaction in there. So then that leads into 3 possible choices of how to proceed. Choice number 1, leave all 119 and 120 in the data set, similar to what I just said, and keep that interaction in the model so that they weren't poorly fit. And you're just going to have to live with them being influential. Now, if I was estimating this model, let's say for a paper that I was writing, in that paper I should say, okay, number 119, 120, hey, these are influential to the model's fit, specifically with respect to the interaction. And just kind of go over what I just said. Well, what happens if I remove that interaction? Then they're poorly fit by the model. So choice number 1, essentially, just have to live with it being influential. That is, of these 3 choices, that is the essentially a last resort. If you think about in general for any kind of data problem, this would be a last resort if you didn't have other alternatives. Choice number 2. Well, we saw that these observations had a common characteristic about them. They are non-20-yard PATs. This is something that doesn't happen very often in football. So, how about we just remove all non-20-yard PATs, not just 119 and 120. How about if I remove all of them from my data set? Re-estimate my model. Or try to find a new model for this reduced data set. Now, when you do that, though, you have to be very careful in understanding the consequences. And that is, this will limit my population of inference. Meaning now that I cannot draw conclusions about non-20-yard PATs when it comes to place kicking. I cannot do that now, because I've changed my data. I have excluded the possibility of getting that kind of observation from the population. But in the end, in the grand scheme of things, it's not a big deal for this situation because, again, non-20-yard PATs doesn't happen that often. Think about, if you were doing this model for a football coach. Would the football coach really care if you can't draw inferences to the non-20-yard PATs? Probably not. So that's choice number 2. Choice number 3. Well, maybe there's just a fundamental thing about PATs in general that we should be considering here, and that maybe I should just remove all the PATs from the data set and build one model for the field goals. And then if you're still interested in the PATs, build another model for the PATs and keep them separate. That is a justifiable approach too. So those are the three options. In order of preference for me, number 2, number 3, number 1. When I was in grad school, I chose number 2. I still think that's the best choice here. Now my co-author in my book, he has a little bit of a preference for number 3 over number 2. But that just shows you how, different people can come up with different models. All 3 of these choices are justifiable. I think 2 outweighs 3 by a lot. But my co-author kind of disagrees a little bit. That's okay. Yes?
Do you include a new variable over there? The new goal is being taken out, so it could not be.
You could. But that new variable, and then you'll get a new beta hat. Do you think that these observations would be very influential towards that beta hat? Yes, they will be. Because it doesn't happen often that there's a non-20-yard PAT. And essentially, essentially, that's what this interaction is already doing. Essentially, it's just exactly what you just said. Yeah.
In your book model, the estimate for PAT also changed?
Yes, it did. And that is just because of that interaction, too. Okay? That's why. So I have a little bit of more of a discussion on page 101 about this. For me, when you compare, let's say, number 2 to number 1, overall there's only 13 times in my data set where I have a non-20-yard PAT. It's really tough to base an overall conclusion about what exactly is this effect of having a non-20-yard PAT just based upon 13 place kicks. And so that's why I felt that rather than leaving that interaction in, leaving 119, 120 in, I thought it was best to just put all non-20-yard PATs aside and not even worry about that. Because I don't know if what I'm seeing here with the data is an anomaly or maybe a real trend. So that's why I thought, okay, number 2 is better than number 1. Now, with respect to number 3, if you believe that indeed PATs were, let's say, something like substantially different than what was happening with field goals, then that would make sense. In terms of, let's put it in terms of our model. Let's say, what's a good example? Oh, this isn't the best example, but I'm going to use it. So remember we had altitude, and we got rid of altitude, early on in the modeling building process. But if you felt that altitude had a different effect on PATs than on field goals, keeping everything else equal, then okay, number 3 would make sense. I don't. I think PATs and field goals are very, very similar to one another. I mean, the same process is being used. You're hiking the ball from the center. You're still trying to kick it through the uprights. The defense is trying to block it. Okay? They might not be trying to block it as much as for a PAT than a field goal. Well, that's what's represented essentially in the PAT variable in the model. And what you'll see, PATs have a higher probability of success, and you can prove it, than field goals. So that's why I chose model number 2, or choice number 2, I should say. Okay, so here's a big note. Removing observations from a data set, such as what I just did, should only occur when there's very good justification for it. We have good justification here. Just because an observation is an outlier or influential does not mean it should be automatically removed from the data set. And note that my shift 1 key on my computer did not get stuck there. I did want to emphasize this for the following reason. A number of years ago when I was teaching this course, going through the same I went through the same example here, and I gave my students a project where they had to, for a particular data set, find the best model, similar to what we were doing here. And this group that was working on a project, they did those plots similar to what I did, and they saw there was a few observations that were outside those plus or minus 2 lines, and they said, "Oh, okay, I'm removing all those observations from my data set." So they did that. Then they re-estimated the model, and guess what? There were a few more observations that were outside plus or minus 2. They said, "Oh, okay, I'll remove those observations." No justification, just that they're outside plus or minus 2. And I think they went through this one more time before they got tired. And even though in the end, they still had some observations that were outside of plus or minus 2, they decided to move on. Now we know if we know if a standard normal approximation works, we know that about 5% of all observations should be outside of plus or minus 2 by a little bit. But that didn't concern them. And so anyway, that's why I bring this up. You really, really, really need to have justification for removing observations. And then when you do remove them, you need to understand how that affects what kind of inferences that you can make. Here, I cannot make inferences to non-20R PATs. Okay? And for my situations, that's not a big deal. Okay. So, how do I remove these non-20R PATs? It can be a little bit tricky if you're not, if you're kind of new to R still, or if you're new to R, you maybe didn't have experience outside this class. It comes down to, like if you're familiar with SAS, it takes a little bit of time to work with a data set, to understand fully how to work with a data set, to work with data sets, and so on. The same thing occurs here in terms of arranging your data in a certain way. So let's walk through this. I need to be able to identify non-20R PATs. So let's begin by looking at the PATs. So if I execute the code that I just highlighted there, what's going to happen? Does anyone know? Well, I'm sorry. So placekick.mb, if you don't remember, is where my data is. Okay, this has all my observations in it. PAT is my PAT variable. And I do equal 1. Essentially, yes, it's going to give me, this is basically a logical comparison. It's going to give me a true if it's a PAT, a 0 if it's a field goal. Because PAT equal 1 is PAT, PAT equals 0 is a field goal. And so what I'm going to get is a vector of size 1438, because I have 1438 observations, and it's going to be a true if it's a PAT, a 0 if it's a field goal. How about this right here? placekick.mb $distance exclamation mark equal 20. Does anyone know what that's going to do? The exclamation mark means not in R. So it's going to give me a vector of 1438 trues and falses. It's going to be a true if it's not a 20-yard place kick. It's going to give me a false if it is a 20-yard place kick. Okay? So I have two vectors of trues and falses. I combine them with an ampersand, which means and. So if I have two trues, let's say first observation, true and true, meaning it's a non-20-yard place kick, and it's a PAT. A true and a true equals a true. If instead I had true and a false, that's going to equal a false. False and a true is going to be a false. False and false is going to be a false. So, basic logic. So everything that's then highlighted here is going to tell me where the non-20-yard PATs are. But remember, I want to throw those out essentially. I want to keep everything else. So what I do is I use my exclamation mark again to basically change the trues to falses, the falses to trues. So now, since I'm putting that in my row indice here, so notice what I'm doing here. I have placekick.mb, and I'm going to tell which rows do I want? Well, I want the rows that are non-20-yard PATs. I'm going to put that into a new data frame called placekick.mb2. And that's how you extract or throw away, you could say, all the non-20-yard PATs. If this isn't totally clear, what you should do then, of course, after classes, highlight the code, certain segments of the code to see what happens and run those segments of the code. And that's, again, how you learn how to use R or any kind of software package to some respect, where you have programming involved. So that's how I can pull out all the data that I need. Any questions? Okay, so now I have 1,425 observations left. Back in chapter 2, when we were doing working with the place kicking data set, this is how many observations we had. So the chapter 2 data for chapter 2 version of the place kicking data set is now what we have. And so now you have just a general idea of why I chose to give you like a little bit of a smaller data set to work with in chapter 2. And then in chapter 5, now we're looking at the entire data set essentially. Okay. So now that I have my new data set, guess what? I need to go through all that modeling process again of choosing the variables, looking to see if I need transformations, looking for interactions. I need to do all that again, unfortunately. But as you might expect, since we removed very few observations, our model that we get in the end is going to be essentially the same as what we just saw, but without the distance and PAT interaction. So that's good. So what I do here is I just put the data into the explanatory variable pattern form again, similar to what we've done. I estimate the model. Here are all my beta hats. I use examine.logistic.reg to assess the fit of the model. And then this is what I get on page 104. So it's a similar looking plot to what we saw in the past. Look at the deviance divided by df, kind of small, so that's good, close to 1. We really don't have any large, let's say an absolute value, standardized Pearson residuals. You might be thinking, oh, wait a second. Didn't we have this issue before where we had something that was way extreme on the Cook's distance plot? Well, yeah, we did, but you have to take into account the numerical scale. Before, the y-axis top was about 0.3 or 0.4, and we had an observation that was way up high there. Now it's only 0.15. Oops. Just verify that. Yeah, it was 0.3 before. So this was, the highest point was 0.3 before. And so, but you might be thinking, okay, wait a second, well, there's 116 now. Hey, shouldn't we might be concerned about that. Well, this is where, similar to what we did before too, you go back to the original data set. You look at every single observation that is essentially being pointed out by these plots. In 116, that has over 600 place kicks in it. It's the 20-yard PATs, or most of the 20-yard PATs. I would expect an observation that has over 600 place kicks in it to be influential. So I'm not concerned about it. You know, we have some other observations that are kind of sticking out too. And so what I did was, and the code is in my program, I took them out one at a time because I didn't see any kind of characteristic about them that made them similar to one another. I just took them out one at a time, and I looked at the model. Did my model change much? In the end, it did not. So therefore, I am not concerned that these, I don't think that these are really influential. So that's good. Do note that the numbering on these plots here, the observation numbers change corresponding to what we had with the previous data set with 1,438 observations, because I have removed some observations from the data set. So in the end, this is my model. Any questions? Okay. So another thing that you could do, which is not in my book, not in my notes here, I just simply took it out due to time considerations, is as follows. And if you've had like a Stat 870 course, this should sound familiar. So I actually collected more than 1,438 observations. I collected information, and this was in 1995, on pretty much every place kick that was attempted that season. For some reason, in Oakland, I couldn't, kicks that were done in Oakland, I couldn't get information on. But otherwise, I got every other place kick. And there was over 1,800 place kicks that were actually attempted this particular season. Since I had such a large data set, what I decided to do was split my data set into two parts. A data set that's often referred to as a model building data set. Some people might call it a training data set. And then another data set that is often referred to as a validation data set. So I can try my model out on to see if it works. So this 1,438 observations before that you've seen, that was my model building data set. That represented about 80% of my data. And so all I did was I used a mechanism to randomly select 80% of my observations. Then the remaining 20% of my observations went to my validation data set. Now at this stage of this process, what I can do is try this model out on my validation data set. And the way that you could do that is to re-estimate the model based upon just for the validation data set. So take these exact same terms, re-estimate the model in the validation data set, and look at the beta hats. Do they change a lot? If they do, that should be a concern to you that maybe your model won't work well in actual practice. You know, let's say I want to predict for now the next season. Maybe my model's not going to work well because I'm getting something totally different. Another thing that you could do is form Pearson residuals. So take this model here, and then for every explanatory variable pattern that you see in the validation data set, estimate pi hat. And then form a Pearson residual. If your Pearson residuals are outside of like plus or minus 3, then that should be a concern to you. Or potentially that could be a concern to you because that is representing that maybe that observation not being fit well. Subject to the usual concerns of, you know, is a normal approximation going to work? So that's what one could do. If you want to see the details, get my master's project report that I wrote out. If you want to know more about model building and validation, it's basically the same concepts as what you will learn again in Stat 870. In my Stat 870 notes, it would be, I think, section 9.6, if you want to see that. Okay, so now that I have the model, now I can use it. So you want to interpret the model. So this is, I think you could say, good practice then for the final exam, because you probably will have an opportunity to interpret a model. This should all be reviewed. So we're going to kind of go through it quickly. I won't go through all the details. Oops, close that out. So here's my paper on this data set, published a number of years ago now. This was my very first paper ever published, and it's the only time that I ever started a paper with a poem as well. In fact, it's the only time I've ever seen a statistical paper starting with a poem. But anyway, it fit the circumstances. Thank you for the musical background there. Okay, so what I would like to do in the paper, and I hope you do take time to read it, it's a nice summary of this data set. What I'd like to be able to do next is to reproduce this table of odds ratios, because now that I have the model, I would like to understand better the effect that a particular explanatory variable has on the response. And so again, we have change, we have PAT, but remember we also have the distance and PAT interaction. So because of that, if you notice I am, oops, come on. Oh, come on, give me my pen. There we go. I am looking at for a 10-yard decrease in distance with when set equal to 1. Also, I'm looking at a 10-yard decrease in distance with when set equal to 0. Also, let's turn things around. Suppose I look for an odds ratio comparing windy versus not windy, but then I have to set distance to a particular value. And so to do that, if you remember, we can use MC profile package. In my paper, I use 90% walled confidence intervals. I'm going to use 90% profile likelihood ratio intervals here. In my paper, I use SAS to estimate the model. Here I'm obviously using R. And so because of that, there will be very, very small numerical differences in some of the estimates. And to look at these odds ratios, since I have so many odds ratios that I am looking at, I decided to make this a little bit more fancy in terms of the labeling. So the odds ratios I'm going to look at in order, I decided to create labels. So the first one's going to be for change, the next one for PAT, last one win versus not, the win variable at a distance of 60 yards. And also to help me out too, I decided to create an object that contains, you could say, the variable name in order of the beta hats in my model. So of course the very first beta hat of my model is the intercept. So I have int for that. The next beta hat was for distance and so on. Next what I do is I create my matrix of basically coefficients for my betas to form these odds ratios. So for example, for change, my odds ratio of course would be E raised to the, my estimated odds ratio would be E raised to the beta hat, let's see, 0, 1, 2, 3 power. For change versus not no change. Remember what that change represents is essentially for pressure. And so, let me show you here. Oh, no. Well, maybe I won't show you. Oh, I already had run the code, so why don't we just look at it this way? This will work just as good. So this matrix K contains all the coefficients I need. Please make sure you understand how to form that matrix K. The one thing that we are doing differently from before is I use my dim names argument in matrix, which we haven't seen. And in a list object, I put, okay, I want my rows to be labeled by or.name and my columns to be labeled by var.name. And so then this is what I get. So for the change variable, I have a coefficient of 0 on beta 0, coefficient of 0 on beta 1, coefficient of 1 on beta 3, and coefficient of 0 on beta 5, for example. And so all these nice little labels, the dim names thing, helps just label stuff and make it look a little bit nicer. Then I use the MC profile function. I then use confident, and then using the exp function itself, I get basically what's my table of odds ratio. It's very similar to what you saw in my paper. And so what do we see here? Well, for example, look at change. It has an estimated odds ratio that's less than 1. Notice the confidence interval for the true odds ratio is less than 1 as well. So what does this say? Remember, change equal 1 corresponds to a lead change would occur if successful. Change equals 0 corresponds to a lead change would not occur. Remember, change is measuring pressure here. So what is this saying here? Do you think there is a pressure effect? Yeah. Because the odds of success when change is equal to 1, that's in the numerator, is less than the odds of success when there's not a lead change, that's in the denominator. The odds ratio is less than 1, meaning the numerator is less than the denominator. So we have marginal evidence of a pressure effect. Let's look at distance. So if I have a 10-yard decrease in distance, what's gained by that? Essentially, we're looking at. And let's say it's windy when we're assessing this. Look at the confidence interval, 2.8 to 12.97. So what this is saying is that the odds of success are higher when your distance goes down by 10 yards than, the odds of success is higher when the distance goes down by 10 yards. That's when it's windy. Look what happens when it's not windy. Odds ratio is 1.86, 2.7. We have the same conclusion, but notice the amount of benefit from a 10-yard decrease in distance is less. Hopefully that makes sense. You know, if it's windy out there, you want to be as close to the goalpost as possible. So that's why there's more of a benefit, because there's less time that the wind is going to have a chance to affect the ball in its flight for shorter distances. That's why you see this. Now let's look at, let's say it's wind, let's look at the wind variable. So I'm comparing the odds of windy versus not windy. Distance of 20 yards. Look at my confidence interval, 0.77 to 16.24. Ah, 1 is inside that interval. So would you really be concerned about if it was windy or not if you're doing a 20-yard place kick? No. 30 yards, similar. But now at 40 yards, look what happens. Now my confidence interval is completely less than 1. So what that's saying to me is that, again, I'm comparing windy versus not windy. So windy's in the numerator, not windy's in the denominator of those two odds. So that says the odds of success are higher when it's not windy than when it's windy, since the odds ratio is less than 1. And we can see that same trend occurring. Oops. We can see that same trend occurring throughout there. It's becoming less and less than 1. That again occurs because of this interaction that we see. The longer the place kick, the more it's going to be affected by the wind. Well, what about 20-yard place kicks? How about we focus on 20-yard place kicks and we find the probability, we try to estimate the probability of success for them. And we use profile likelihood ratio intervals too. So what I decided to do was for this situation, let's see now. Let's say PAT is 0, change is 0, wind is either 1 or 0. Let's see. No, I'm sorry, I did not get that right. I apologize. Let's see here. I'm sorry, I'm comparing wind is equal to 0, change is equal to 0. I'm fixing those. Looking at 20-yard place kicks, and I'm comparing PAT versus not PAT. Sorry, PAT versus field goal. So this is, then it is a PAT, it is a field goal. And so I use the MC profile in much the same way as before. Here are my estimated probability successes for PAT 0.984, for field goal 0.947. Same distance, same conditions, these are being kicked at, but different estimated probability successes. And then look at the confidence intervals. 0.976 to 0.991 for PAT, 0.921 to 0.966 for a field goal. Notice the intervals do not overlap. And it's that's kind of an ad hoc way to say, yes, there is an effect here. That this, PAT versus field goal, it does matter. Because the probability successes are different. So I think that's an interesting finding. Yes, the probabilities are still high, yes. But I think it's still an interesting finding. And if we would have went with that choice number 3 about how to approach this modeling in terms of remove all the PATs from the data set, you couldn't make any kind of really comparisons. Now, if you've taken a look at the paper, you also note that I focus on a particular place kick that was done by Lynn Elliott, who was the place kicker for Kansas City Chiefs. And this was back in 1995. I was, of course, in grad school at the time. It was Kansas City had a great regular season that year. They had 13 wins, 3 losses, #1 seed in the AFC playoffs, home field advantage throughout. And they played, in their very first playoff game, they played the Indianapolis Colts, which I think had 8 wins and 8 losses that season. Everyone thought Kansas City was going to win. But with 4:12 left to play, the score was 10-7. Indianapolis was winning. And so Kansas City got the ball back, they drove down the field, and they gave Lynn Elliott one last chance at a field goal. If he's successful, the game's tied. The game will go in overtime. If it's a failure, the game's over. Kansas City's great season is over. Let's see what happens. Now, this was recorded with a VCR, if you remember what those are, so the quality's not the best. But if you have problems seeing the ball, just look at what the referees do here underneath the goalposts. Oh, wide left. Oh, poor Lynn Elliott. By the way, that was the last time that he ever kicked in an NFL game, too. He was released from the team that season. He had a few other opportunities with other NFL teams after that, but he never kicked in an actual game again. So in that situation, for Lynn Elliott, poor Lynn Elliott, was a 42-yard field goal. It was not windy. It was a pressure kick. Change was equal to 1. And of course, it was a field goal. So what was his estimated probability of success? So what we can do is similar to what we did before. I get an estimate of 0.685. So about 2 out of every 3 kicks under those conditions, on average, are estimated to be successes. Unfortunately for Lynn Elliott, I guess you could say he was that 1 out of 3 that are estimated to be failures on average. Here's also my confidence interval as well. So anyway, kind of interesting to see that. So again, this is the season, that video is from the season that I actually collected the data. So this was after I saw that, which was probably early January, and I was basically just had collected the data, and I was getting prepared to further investigate the data. So that was my incentive then throughout my rest of that semester, was to build my model to figure out what was Lynn Elliott's probability of success. Should I really be upset with Lynn Elliott for screwing the season for Kansas City that year? Anyway, and you know, with binary outcomes, sometimes it works, sometimes it doesn't. Okay, so also in my paper, you're going to see some nice little plots. These were done in SAS. There we go. These were done in SAS. I recreated them, of course, in R here. And what I decided to do was, suppose that we had a field goal, and let's plot the estimated probability of success versus the distance. And since I have other explanatory variables that are binary, what I can do is just simply represent their effect by different lines in my plot. So the red line here represents when change is equal to 0, when is equal to 0, here's the estimated probability of success. You can think of this as, let's say, the least risky circumstances for a place or a field goal. And you can see there's the estimated probability of success as a function of distance. But when I add a risk factor, such as the place kick is done under pressure, we can see the effect that it has. It lowers the estimated probability of success. And we see this effect further. Let's say change was 0 again, but now I add it's windy. Well, remember that interaction that's in the model, and look what happens. It's for those larger place kicks where wind becomes a factor that lowers the estimated probability of success. And then in the situation where I have, let's say, the most risky place kick, where there is pressure, it is windy, you can see again what happens to the estimated probability of success. So a nice little graphical portrayal of what my model is actually saying. And then lastly, I do another little plot that shows the same thing, where the red line again is change equal to 0, and wind is equal to 0. The purple line is the opposite, where change and wind are equal to 1. So least risky versus most risky, and I put 90% confidence interval bands for the probability of success around them. And again, you can see that there are differences. These you don't see an overlap anymore after about 38 yards. Okay, so any questions? Okay, well, I think that is a good stopping point then.